So today we will continue our discussion on the NAND flash, and then let's talk about the scaling challenges for the two-dimensional 2D NAND flash. And the last lecture we already talked about the cell-to-cell interference. So basically, as you scale the dimensions, those floating gates VLAN pitch become smaller. So the cell is capacitively coupled to the neighboring cell. So as you program this cell, then some of the programming voltage may drop across to other cells through those capacitors. So here we show the interference increases with scaling, and we will show you more details in the next slide. But this is the first challenge. Second challenge is this few electron problem. The number of stored electrons reduces, right? Because you only have like 10 nanometer or so floating gate area. Then the number of electrons you store there will reduce. So here you see the scaling trend. As you move to sub 2 nanometer node, you may only have a dozens electrons there. So any fluctuation in the number of electrons will result in a VTH shift. Then that's tricky. So here's some closer look at this cell-to-cell coupling issue. So here we have those cell, and then the neighboring cell, there will be like 8 neighboring cells. So here then, of course, depending on the directions, you may have the bit LAN to bit LAN coupling, or word LAN to word LAN coupling, and also the diagonal, which is less a concern. So mostly it's like, bit LAN to bit LAN, word LAN to word LAN, and then you have a diagonal. But you have to add them together. So then the total coupling. So it's like more than 20% of your voltage applied, may apply to other cells. So what does that mean? That means you will have the VTH shift. If you recall, we have this order for the programming, right? So erase is a block erase. That's okay. But then for the programming, we do page by page or row by row. So you do word LAN 1 first. So here cell 1 from word LAN 1. You do the programming. You have the bias scheme we discussed before. So you do the programming, okay? So then that's fine. But the problem is when you do the adjacent cell, that means a cell 2, the word LAN 2, you're going to apply this 20 volts on top of that. Because this floating gate, now the coupling is so strong because the distance is so small, you have this large parasitic capacitance. So some of the voltage will drop on this cell, right? So this will, shift the VTH because you've got more electrons injected to the floating gate. So this is the coupling issue. If you look at the distribution, right? So here, for example, your target distribution, this purple one, that is after the programming, then you have this purple distribution. But then if you do the programming of the next or adjacent bit LAN or adjacent word LAN, then you will measure what is the VTH of your previously programmed state. You see there's a shift right here towards the right because you have more electrons injected after you program the adjacent cell. That's a problem, right? So here, if you look at the VTH multi-level operation, then that means you have shift of the VTH. Then the gap becomes smaller. So you may have some errors. So this is a big problem for the multi-level operation, especially for sub 20 nanometer load. This become very significant. So here, what is the fundamental cause for this coupling? So if you look at the geometry of the floating gate, this is a cross-sectional view, right? So previously, the floating gate actually is a polysilicon, right? Polysilicon. So actually, it has certain heights. So here we have the ternal oxide, and then this IPD, interpolydielectric, and we have a control gate, which is VLAN, which is shared. So from this floating one cell to another cell, you have certain, actually, two, let's see. You have those coupling. So here, you want to reduce this coupling. Then what you can do, of course, is to reduce the cell height, right? So because this capacitor, proportional to the overlapping area. So here, then the general trend is to, if you want to improve this coupling, or let's say mitigate the coupling, then you want to make this floating gate height smaller and smaller, and eventually this will migrate to this planar structure. Okay. So then your floating gate and floating gates will have minimal overlap. So here you see that as you reduce the floating gate height or the thickness, then you're going to reduce this VTH shift. However, this may cause some trade-off. Because here this coupling actually determines this alpha CG. Okay. If you recall the gate to control gate to the floating gate coupling, right? So yes, you reduce this parasitic cap between cells, but also at the same time, you reduce the coupling from the control gate to your floating gate. That means your programming voltage will become higher and higher, right? Because the coupling ratio we discussed before, right? You apply 20 volts, maybe only 10 volts actually drop on the floating gates. So if this coupling ratio becomes smaller, then you may need to apply 30 volts to get the same voltage drop on the floating gates. Because fundamentally, the floating gate voltage potential controls the underlying channel currents, right? So there's a trade-off like this. Then what are other mechanisms to reduce the coupling? Of course, then if you recall in the DRAM lecture, we talked about the air gap to reduce the parasitic bitline capacitance. So here, similar strategy, right? So between those floating gates, if you can, remove this dielectric, make a void with the air gap, then you can reduce the capacitance in between, right? Because air has a epsilon close to 1, which is a, like vacuum. So that's the lowest dielectric in between. So here are some images showing the air gap. And then if you do that, you see that the distribution will be suppressed. I mean, on the right tail, then the air gap will be more, tightened because you have less shift towards the right compared to the silicon nitride, which has higher dielectric constant than silicon dioxide, and then air is the lowest K value dielectric. Of course, then this adds some process complexity. You have to etch this material. So air gap has been used for sub 20 nanometer 2D NAND flash. Okay. So then let's move on to the few electron problem. So retention will degrade, right? So here we show the number of electrons you may have. At 90 nanometer, you may have 1,000 electrons there. But then at 35 nanometer, you may only have 200 electrons. And then, as I said, for sub 20 nanometer, you may only have like 30, 40 electrons. So here then the fluctuation of those number of electrons will lead to the fluctuation of the threshold voltage, right? So the delta VTH directly depends on the electron, the charge in the floating gate divided by your CK, which is the C interpoly dielectric. So any shift, right, will change your threshold voltage. So here we show and also for the multi-level cell, then the retention time will become even smaller due to this few electron problem. Because the margin between the threshold voltage, right? If you have multi-level cell, then the margin is so small, so any shift will cause the error. So it's very hard to manage with fewer electrons. And also on top of that, we may have this RTN noise. We talk about the RTN, random telegraph noise, when we talk about the SRAM logic transistor. But here in the flash transistor, this may also happen, right? So some of those electrons may temporarily trapped to the interfacial trap and then release back. So your threshold voltage may have temporal shift. And as you scale, then you may have this dominant trap, and then your RTM will become even more significant. So basically, you add temporal noise on top of your VTH distribution, right? Your VTH distribution already has a spatial, variation. On top of that, then when you measure at different time, you may add additional noise. Then that means this distribution may become even wider. So that adds the challenges, right? Because you have this multi-level states, you care about the margin or the gap in between. So those are the challenges when we scale the flash transistor. So that's why there's no solution beyond 10 nanometer in the two-dimensional NAND flash, because those problems become so significant. That's why we need new solution. So we will talk about the recent trends. And the first one is the charge trap cell, and then we talk about 3D NAND. So the charge trap transistor, okay. So far, we mostly talk about the floating gate transistor in the 2D NAND. But actually, recently, the NAND adopted the charge trap transistor instead of the floating gates. So what's the difference here? So the operation principle is the same, but then there are some minor differences. So if you look at the floating gates, we talked about before, so you have the polysilicon as a floating gates, and then you have two oxide. One is ternal oxide, one is interpoly dielectric. So here in the charge trap, the key difference is that the floating gate material is changed from the polysilicon to the nitride. Okay, so here this blue layer is nitride, silicon nitride. So if you look at this direction, you may have the sonus structure, SONOS. You may still have polysilicon top gate, control gate, and then oxide, nitride, oxide, and then silicon. So sometimes this is called the sonus structure. Okay. So the key difference is changing from the polysilicon to the nitride. So here, if you look at the motivation, so in the 2D NAND, or let's say even 2D NOR flash, if you change from the polysilicon floating gate to the Sonos structure, you could have lower programming voltage, okay, and could potentially offer longer endurance cycles and better retention. So this is because you have to look at the band diagram, and here the silicon nitride, right, and it has potentially many trap sites for the electrons to stay in the nitride layer. And the one critical, or let's say one key difference between the polysilicon floating gate versus the nitride is that the polysilicon, this floating gate, is conductive. It's conductive. That means, okay, the electrons in the floating gate can flow. The electrons are kind of movable. Electrons here are movable. Or in other words, if you have some leakage paths here, then all the electrons may, move one by one, and then eventually all of them may get lost. But then in the solar structure, the silicon nitride is more like an insulator, okay? Right. It's more insulating. So those electrons are individually trapped, okay? If there is a leakage path to remove one electron, the other electrons will not follow because each individual electrons are trapped by itself, okay? Unlike the polysilicon, silicon is still kind of conductive, right? Compared to the silicon nitride in terms of band gap and so on. So silicon is more conductive. So silicon nitride, you will have the limited charge loss. So there are some advantages like that. So here are some more details about the erase and programming. Mostly the same as the floating gates. If you use the channel FN tunneling, this is similar. Okay. So program, for example, you apply here maybe a little bit lower voltage, like 7 volts on top, and then you get the electron injection through the channel FN tunneling, and then erase. You reverse the voltage. Let's say negative 7 volt on the gates, or you can apply positive 7 volt from the substrate. So here, the band diagram between those program erase is showing here. So there are trap states in the nitride where the electrons will be stored. But one key difference here is that in the erase, so actually both carrier types, electron and holes, are involved. So if you recall the floating gate before, with mostly only electron move in and move out, only electron, right? But in the Sonos, holes actually also can move. So here, for example, here in the erase state, you see the holes can also do the FN tunneling and tunnel into that. Electrons, of course, can tunnel out. But this is more efficient than just the electrons moving out. If holes move in, will recombine with the electron. So it's like equivalently you get out one electron from the nitride. If you get one hole in, it's like equivalent to get one electron out. So the reason is that here, if you look at the barrier height for the, I believe for the electrons here, for the holes are not that high. So here, but still seems a little bit high. But why would this claim that, holes will be involved? Close, I mean, the barrier height is still higher than electrons, right? But typically, people will claim that in the Sonos structure, hole injection is also involved. But still, the majority is electron, but the holes are involved. So this is important later when we talk about the 3D NAND flash, because hole injection is needed for the erase. But anyway, here is the conclusion. So here the holes are also involved in the erase. Okay. So there are changes actually for the nitride-based charge trap transistor. So it was proposed a long time before, even at similar time, like the floating gate, polysilicon floating gate transistor. But until recently, so then we changed to this metal. Used to be Sonos, right? The top control gate is still polysilicon. But recently we changed to the metal, okay? It's metal oxide, nitride oxide silicon. And then the silicon may become polysilicon when we switch to the 3D NAND. So this is like the structure today. So this becomes a mainstream technology for the 3D NAND flash. We are going to discuss in the next. Okay. So 3D NAND. So as I said earlier, so then the 2D NAND scaling face challenges. And then in the year around 2013, 14, 15, around that, then the 2D NAND scale to like 15 nanometer or so. And meanwhile, then the 3D NAND flash become introduced in the industry. So here then after that, then 2D NAND scaling stops, then the 3D NAND take off, okay, with higher and higher number of stack. So then this transition is around this 2014, 2015, around that time, almost 10 years ago. But the R&D actually started earlier. So when I say 2014, 2015, that is when the commercial product become available. But in terms of the R&D, the research and development, this was started way before that. So the first known paper in the public domain was published by Toshiba in BiCS Symposium 2007, this BiCS structure. We're going to discuss this paper in the next few slides because this was regarded as the milestone, I mean the first breakthrough of the 3D NAND technology. And credit goes to Toshiba. And if you recall the history, Toshiba also invented the 2D NAND in 1980s. So then in the 2009, there's another important paper from Samsung, also in Symposium VLSI. And also Toshiba improved the design, but Samsung jumped into this business by publishing this TCAT architecture. And then after that, there are different proposals by different companies. But then Samsung becomes the first one to commercialize the 3D VLAN, as I said, around 2014. So you see from the R&D to the product, it takes like 8 years or so, or maybe more than that, because even before the first publication, there's maybe internal research as well. Okay, so then let's talk about the 3D NAND flash. Actually, there are different ways to do the stacking. So here, this is all monolithic stacking. Okay, I have to emphasize, this is not the bonding. Okay, this is not the packaging stuff. This is monolithic. Monolithic. That means you're going to deposit the materials sequentially, layer by layer. It's not you have two chips, two wafers you are going to bond. So this is a sequential. So here then there's a simply stacked version and not simply stacked version. Okay. So the idea is to take advantage of the third dimension, right? So if you do a simple stacked NAND flash, that means you're going to repeat the 2D NAND flash process layer by layer. So you make the first layer 2D NAND flash, then you make the second layer, third layer, fourth layer, fifth layer, and so on. So this is not good. Okay, even though you use the same silicon footprint in terms of substrate area, but then the cost is still very high when you do this fabrication. Because I have to emphasize the most cost-effective step in the manufacturing, no matter it's logic or memory, is the lithography, okay? Or the number of masks you're going to use to do the fab. So if you do this simply stacked NAND flash, you're going to repeat the same process layer by layer. So you do not save the lithography step, right? So if the one layer NAND flash, you need 10 litho step. If you do 2 layers, you need 20. 3 layers, you need 30. Then you only save a little bit on the silicon substrates wafer costs, but that's a small portion of the entire manufacturing. The most, let's say 80% of the cost is here. So what is the cost-effective solution for the 3D stacking? That is to share the lithography step, regardless how many layers you are going to stack. That's the key concept of this one. So actually, there are different ways to do this 3D stacking. There's a proposal of this horizontal channel, but you are going to share the gates, vertical gates. So here you still have the channel, but you are going to share the gate like this. It will be similar to the, actually, this one is similar to today's stack nanosheet for the logic transistor. But at that time, we don't have the stack nanosheet for the logic. So this one, if you do that, it's more like the stacked nanosheet structure. You're going to share the vertical gates, okay? And then another approach to rotate the channel by 90 degrees. Now the channel is vertical. You are going to have the horizontal gate. It's like a channel all around. Okay. So this is then becomes the mainstream. We are going to discuss in more details. But in principle, you have two ways to do the stacking with a cost-effective approach. One is horizontal channel, vertical gates, or vertical channel, horizontal gates. Okay. So here, actually, there are many pathways, right? If you want to stack memories in 3D, monolithically 3D. So here we have the, let's say, simply stacked version. As I said, when you stack more layers, you're going to repeat the mask step. So here, but then there's a, research on that. And actually, later when we talk about the phase change memory, when we talk about cross point memory, the 3DX points by Micron and Intel, is this approach. Okay, you're going to repeat this patterning layer by layer. Okay, it's like a cross point memory stacked vertically, layer by layer. Okay, so then this is for the 3DX points. But for NAND, nobody uses that. Then the NAND is all vertically shared something, but then you're going to have two pathways, as we just discussed, either vertical channel or vertical gate. So if it's vertical gate, then your channel will be horizontal. It's more like a stack nanosheet, right? Stack nanosheet, then your channel is horizontal, but then you share this vertical gate across multiple channel. There was like early papers by Macronix, a Taiwanese company, on this vertical gate NAND flash. But then the mainstream is this vertical channel here. But even within the vertical channel, there are two pathways, okay? Depending on the process flow. One is gate last, one is gate first, or word line last, word line first process. This is similar to the logic transistor. You have the gate first and gate last process. So if you recall the logic transistor, I don't know if I talked about that before, but the logic transistor, when you do the gate, like the polysilicon gate, it's like gate first process. You first deposit the polysilicon and then you dope the drain and source and drain. It's gate first. But then when you switch to the high-k metal gate in the logic transistor, is a replacement gate, the gate last. You have some poly gate as a dummy, and then you use that to form your source and drain. And after that, you remove the dummy gate, that is like a sacrificial layer, and then you redeposit your high-k metal gates. Okay, so similarly here, for the floating gate, not floating gate, I mean actually this one is a floating gate. If you still do the gate first process, then you can use the floating gate, okay, for the 3D NAND. But if you want to do the charge trap, CTF, charge trap, then you have to use this gate last process. So at the beginning of the research, I mean, different companies have different views. So here there are two parties, right? So here then Intel and Micron used to joint develop the NAND flash technology. So they share the same facility. There is even a joint consortium, IMF or something. I forgot the name. There is a joint company by Intel and Micron. But later, you know, like a few years ago, they split. But initially they are together, okay. And Macronix is also doing that. But then the other companies are doing this gate last, including the Toshiba. And Toshiba, you know, used to be with SanDisk. It's like today, Kioxia is with Western Digital. You know, Toshiba and SanDisk are predecessors of the Kioxia and Western Digital. And then Samsung and SK Hynix, okay, they are on this CTF track, gate last. So this is at the research stage, but eventually what becomes the final product, okay? So then this is another, I moved one page, okay? So here I showed earlier, okay, the cross point, this is phase changing memory, 3DX point become a product. Of course, then this product, you know, failed later, but at least it was on the market, okay, for a few years. So then Intel also managed to do this floating gate first process before Intel, you know, sold the memory business to SK Hynix. Intel has a product on the this kind of SSD, okay. But the majority of the vendors go with this gate last process. Even Micron, you know, abandoned Intel and then joined the other party. So all the major vendors are on this gate last process. Okay, this is the mainstream. So we will talk about the first paper, but before that, you know, you can buy those from the market. And then let's talk about the first paper, because this one set the foundation for all the following innovations. Even today, I mean, if you look at the fundamental architecture, it's the same one as this one, published by Toshiba. So as I said, this is Symposium VLSI 2007. And in this paper, Toshiba proposed this bit cost scalable technology they call BiCS. Even today, they use this BiCS as their brand. Okay. So why this is bit cost scalable? Because they're going to share the lithography. Okay. So the fabrication is done by, I will show the fabrication step later, but let's look at the structure first. Or let's say the features first. So here, the channel is vertical, and what is the channel material? It's polysilicon. Okay. Polysilicon is used as a channel instead of, in 2D NAND flash, the silicon substrate, which is a single crystalline silicon, used as a channel. So here, switch to polysilicon, and then the program is still by the normal FN turning and erase. So here, the Guido current and the hole injection is important. And then what is important here is to understand this 3D architecture as we show here. And at the first demonstration, it's like a 3F by 2F, but actually in principle, you can do 2F by 2F from the top view. But in this initial paper, it's like a 3F by 2F, but later people can improve that to 2F by 2F. So what is important here is, let's look at one string, okay? Now it's like vertically standing up. So here you see the structure. You have the polysilicon, and then you have the charge trap layer, this ONO layer, this like purple one. And then you have the, in this case, polysilicon gate, this initial version, but now we switch to metal. But this initial paper is polysilicon gate. Okay. So if you look at the schematic, and let's say net list, it's like you have this string vertically. The top one is a string select. The string select and the ground select. Okay. In the middle, you have those charge trap transistors in series. So this is just one string, but if you look at the 3D, then it's important to understand this 3D net list. Maybe I should have that in the next slide. Okay, we have some zoom in, so we can move to the next. So here, again, this is some zooming pictures. So here, you have many strings here, okay? Then at end of the top string, you have the bit lamps like this way, okay? And then where is the word line? Word line is the horizontal plane. You have word lines here. This is word line. And then, of course, as I said, the very top layer and the very bottom layer is a string select for the NAND string, top and bottom. And then here, what is important? You see there's staircase like this. This is word line staircase, because you have to make connection to each different layers to select which word line or which control gate you are going to select. So you have to make this contact wire to different layers. So this part is called the word line staircase. Okay. So this is a structure. So here are some zoom in. I already showed you that. I will skip this one. So what is important is this one, okay? So you need to understand this net list. You also have that in your homework. So here, the word line, as I said, each plane is going to share one word line. But then how do you differentiate different string? That is here, the upper string select is separate. This one is separate. Here is a common. Okay. So you need to have the XYZ decoding to locate individual cell, because now it's a three-dimensional structure, right? If you want to program this cell, then you need to select first this bit line, right? Second, this VLAN. But this VLAN also control other strings along the same bit line. So you need the upper string select to be separate. You only turn on this one. Oh, sorry, we are looking at the middle one. So then you only turn on this one. Then this whatever ground voltage can deliver to this guy to program. Okay, so you rely on the VLAN, bit line, and this upper string select to locate the cell. And the bottom string select actually could be common. Okay, you can share that. So you just need to separate the top string select. So any questions here?
At the lower string select, if we are using upper string select to distinguish frequency.
No. So it's not for the selection of the location. You have to recall in the 2D NAND flash, we also have the bottom string select. That is to float the entire string, right? So actually, if you look at this 3D net list, if you cut, let's say you take one slice of this one. This is the very first slice. If you cut it, it's exactly the same as 2D. Right? It's like you have many slices. So it's just the 2D, you have 2D and you make it vertical, one slice, and then you add many slices. Okay. This is like 2D. Okay, so any questions? Okay, so then a few more discussions. So as I said, this BiCS, okay. The key idea is you deposit many layers here, right? You deposit many layers. And then you use one lithography step to etch the hole in between. You are going to fabricate many of those strings. So this is just one litho step, one litho step. This is how you reduce the cost. No matter how many layers you stack, you only use one lithography step to etch the hole here to define that string. So this is good for this memory array region. But then for the VLAN connection here, actually you need to make this contact via access to different layers. It's unlike in the middle, you can etch through all of them together, right? So here, when you make the contact vias, you have to stop at different layers. Of course, the naive way is you do the lithography separately, but that will diminish all your benefits, right? You just want to do one shot litho, but if you separate this contact via fabrication in different litho step, then what's the point of doing this 3D? So here, then the key innovation is that the staircase also just need one additional litho step, okay? So here is the key idea. So this is called the photoresist trimming process, or slimming, or trimming. So here you are going to use one litho step, and this is a photoresist. And then you do your whatever etch, IE etch, okay? You create, but you need to stop at certain, control the etching rate, etching time, and then you stop, okay, at the first layer. Now you do not do additional litho. You are going to reuse whatever photoresist here, but you are going to trimming down this photoresist a little bit horizontally by some chemistry. So you create another like a step here. Then you etch again. Then you will expose the second layer. And then you keep shrinking the photoresist horizontally. And then you do additional etching vertically. Then you can create this staircase. Only one litho is used at the beginning. Okay. This is the key. Any question? So if you look at the staircase, actually it consumes a lot of area. It's kind of wasted, but yeah, this is how it look like. If you have 64 layers, then you have to make individual contact to the 64 layers. You have to, waste a lot of area to do that. So you have to make the contact to each layer. That is your VLAN voltage you have to deliver to that layer. Okay. Okay, so then let's talk about some additional papers. As I said, in Symposium 2009, VLSI 2009, Toshiba published the second generation of this technology, still in research, okay, research phase. But then they managed to demonstrate a 32 gigabits prototype chip. So here in the second paper, what they did is to fold, actually, the two strings like this. Okay, so if you look at the equivalent schematic, it's like that. You are going to fold it. There is like a additional path gate control here, but then the two string become like effectively one string. The reason is that they want to make the bitman on the source line on the top. Previously, the source line is buried to the ground. The source line is buried to the, let's say, the substrate. But then they think the source line resistance is too high because in the substrate, actually, you cannot do metal. At that time, the substrate, if you do source line, is a doped silicon as the source line. So they want to use a real metal. So they have to make this up. Okay. So they have this folded string. But I don't think this is used today for commercial products, but that was a proposal by Toshiba. So in the same year, Samsung also showcased their initial development of this technology. And they call it a TCAT architecture. And then it's pretty much very similar to the Toshiba's design. And there's some subtle difference. For example, here, then they may have the polysilicon is not going to fill entire hole. They will have the polysilicon maybe just surrounding a vertical pillar. Okay, I'll show that in more details later. And then instead of the Guido currents, in this case, use a buck erase. Okay, that's still the erase is from the substrate. So there's some subtle difference, but overall, if you look at the architecture, it's very similar. And also they switch from the polysilicon control gate to the tungsten control gate. So that sounds like a improvement on here and there, but the overall architecture is the same. Okay, so here I'm closer look at those cartoon figures. Right. So here, even though let's say the VLAN will be electrically connected, but actually in the structure there will be, this will be cut into so-called slit. Okay, there won't be a VLAN plane like cover the entire layer. So the VLANs will be split. Okay, and those will be VLAN contacts. But electrically they may be connected. Okay. So here, if you look at the zoom in to this one cell, so this is how it look like actually. So there is an oxide filler. This is a later change to the initial design by Toshiba. Initial design, the entire pillar is the polysilicon, but actually in the recent designs, the core is like core shell structure. The core is the oxide, and then the shell is a polysilicon channel. Okay, and then you have your ONO nitride charge trap layer. So here are some more details on the process flow. So you can view this better. Okay, this is mainstream flow, simplified flow. Of course, different companies may have some, secret technique, but overall flow is like this. So you are going to deposit multiple layers, okay, and then that is the oxide and the nitride sandwiched, many layers. Then one lithography step, one litho step here, right? This litho. You are going to etch this hole. You define this hole by litho, and then etch through many holes where the string will stand. So after you etch the hole, for example, the first one, we see the inner part of the hole, then we deposit this charge trap layer, right, including the channel, polysilicon channel. Of course, you deposit ONO and then poly. So ONO here, and then the green one is the poly. So basically covers the, the surface of this hole. And then you refill the core with the oxide. This yellow one is this core shell. Well, first, you create this shell, right, with those multiple layers, the charge trap layer and the channel layer. And then you refill the core with the oxide. And then here you may etch the snits, decouple the word lamps. And then here, this is the replacement gate, the gate master flow. Okay, you are going to remove the nitride, which is this pink one here. You have an undercut structure like this. You're going to remove this. And then refill the metal. That's why the metal gate is last. The metal, this blue one, you refill the metal like the tungsten, for example. And then remove the additional metal. So only tungsten gate is here, okay? So this is the general flow. Maybe different companies will have some improvements here and there. But as you can tell here, the fabrication challenge now is no longer the lithography, okay? What is most tricky part in this kind of entire 3D NAND flow is the deposition and etching, especially the etching, okay? You deposit so many layers and you have to etch. So the fabrication challenge now move from the lithography, the patterning, to the deposition and etching. So here another slide on Intel's flow, because I said earlier, Intel still stay with, before they stop the memory business, at least 2 or 3 years ago, they still use this floating gate process. This is a gate first process. I'll skip the details. You can look at the flow, which is this from here and then to here. Okay. So here are some key differences between the floating gate and the charge trap flash cell. So in the floating gate, so you see that the floating gate is separate, right? But the charge trap, this silicon nitride layer is continuous, shared, okay? If you recall, we discussed before, the floating gate, those electrons are tend to, move. That's why you have to separate them, right? Otherwise, you cannot distinguish which cell from which cell. But then the nitride layer is okay to share, because then when the electrons inject, the electrons will stay there. Electrons will not move. Okay, electrons will stay locally, unlike the floating gate, electrons will move around. So that's a key difference. And here, holes are important in the touch trap. So in the erase, holes are injected.
Involvement of holes in program of the charge trap?
Not much. I don't know exactly why, but yeah, usually we say that the holes will help with the erase. Program is still electrons mostly. So the program read scheme, this is similar to the 2D NAND. If you recall, we just discussed, we take the slice, right? If you take the slice, then this becomes like a 2D NAND. Okay. So here, the program erase scheme will be exactly the same as a 2D NAND. So for example, here for the programming, you have to select the cell, this string, then 0 volts. And then for other inhibition, for example, you apply 2 volts. This rely on the self-boosting, right? So you play with the timing, and then for the program cell, you apply 20 volts, and then some inhibition, or we pass signal to others. So this will be the same as the 2D NAND. And the read is also the same, right? So you select this one, and then for other cells, you have to have the V pass R to turn on all the cells. For example, 6 volts or 7 volts. So this will be exactly the same. I won't repeat. The key thing is that you have to select that slice, which means this upper string select need to turn on this slice. Okay. If you turn on this slice, this will become the same as before. So here, the erase, a little bit more words on the erase. So there are two erase mechanisms. If the, let's say the channel of this string still attached to the bulk silicon substrate, then you could use this body erase, like 20 volts. Because here, as I said earlier, holes are important. So you need to provide holes. And then in the silicon substrate, you can provide holes if the channel is attached to the bulk of the silicon. But in many cases now, the source NAND, because in here, as I said, your source NAND could be doped silicon, right? Doped silicon. So that's why you will have the body here. But if your string does not have the body, for example here, if the source NAND is metal, actually this is widely used in today's CMOS under array, because nowadays the 3D NAND is fully on top of the silicon substrate, which is used for peripheral circuits. So there's dielectric in between the silicon substrate and then the top 3D NAND. So this is metal. Then here, this string, the channel does not have the body anymore. So in this case, the holes are generated from the Guido mechanism. If you recall the band-to-band tunneling, if you bias this, then if the band is very bent, then you get the Guido current. You generate the electron hole pair there. So this is how you get the holes in this case. Okay. The Guido erase become important. Okay, any question? So let's look at some products. So as I said earlier, Samsung was the first one to commercialize the 3D VLAN, 3D vertical NAND. So this was the first generation of the commercial chip showcased at ISCC 2014. It's 128 gigabit chip. So here, the key feature, 24 layers vertically stacked. And then it has 2 planes, each plane 64 gigabits. And then you see the bit density. So because total chip size is about 133 millimeter square, and you have 128 gigabits. So it's roughly close to 1 gigabit per millimeter square. Okay. So then there are some other like design specs, but if you look at the array efficiency, right, it's pretty good, right? So you have most of those 3D NAND area and some row decoder, and then page buffer and some peripheral circuits, timing control and I/O. So then, of course, then people do not understand what's inside the chip. So then this company, and I think now acquired by Tech Insights. So basically, this one does the reverse engineering. Okay, they bought the Samsung's product and then cut, and under the microscope, they try to look into the structure. So here you see this is very beautifully taken picture under the TEM. So this is a side view. You see this is a string actually. 24 layers and plus some top and bottom string select. But this is actually only a zoom in of this part. So here, let me ask, what is this? Any idea? We just discussed. That word on staircase. Contacts with many word and contacts. Okay. So then this is side view. Okay, they also take the top view to look into here. What is inside this string? So if you look at top view, they have this hexagonal kind of string location. This string and the other string, they are in, in the hexagonal pattern. So here, this is one string, okay? If you further zoom in, this is very high resolution, okay? You can look at the atoms. So you see, you see here the tungsten. Those are the tungsten metal VLAN, okay. And then there's some tinitride layer, aluminum oxide layer, and then ONO. This is a charge trap stack, and then this is a silicon polysilicon channel, and then the core is a silicon dioxide thinner. Okay, so very clear thus the layers. Okay. Any questions? So that means no secret, huh? So here are some like more details on the design. I'll skip some of them. The circuit schematic is the same as before, okay? So the SSL is, they call SSL, okay, string select NAND, separate. So here, the advantage, if you think about this 3D VLAN, first of all, if you change from the floating gate to the charge trap, the floating gate, if you recall, is pretty high in terms of the height of the stack. And the floating gate is kind of conductive polysilicon. So this ONO structure is very thin. So that's why when you do the vertical channel, then you need to care about the thickness, right? Because here you cannot be too thick. That will, otherwise this pillar or this trench will become too large. So you want this to be thin, okay? And then the other advantage is the channel area actually is much larger than the 2D. 2D, you know, is 4F square. And actually the gate is F times F. And if it's the last generation, like 15 nanometer, that will be 15 nanometer times 15 nanometer in terms of the gate area. So that's why you have the few electron problem. You cannot store many electrons there. But in the 3D, you have much larger gate area. Why is that? So first of all, let me ask how to calculate the 3D and let's say the effective gate area for one cell. I think also in your homework. So what is the gate area? You have the gate all around structure, right? So this perimeter, 2 pi r times h. H is you know, vertically from layer to layer. Let's say vertical, it's not from layer to layer, you still have the spacing, but let's say with the thickness of that word line, you have the h, right? You have 2 pi r times h, that is this side surface, right? This could be much larger than this f times f, because typically the h, for example, you can be in like 15 nanometer. I don't know the exact number, so maybe from the image you can reverse engineer, but just give some rough number. This can be 50 nanometer, and this r could be another 60 nanometer. And 2 pi, you know what is that? This one is much larger than your 2D if it's 15 times 15 nanometer, right? So here you have much larger area. You can store much more number of electrons. So that's why here you look at the electrical characteristics of the last generation, not last, the second to the last generation 2D NAND versus this initial 3D NAND. So first of all, the distribution is much tighter in terms of the VTH. And also after coupling, you see almost no shift compared to the 2D. Here, you have the shifting. The reason is that here the coupling is also reduced because from cell to cell, now you have cell to cell, right? The distance now is much larger, which is determined by the edge. It's no longer 15 nanometer. It's you know, tens of nanometer or even 100 nanometer. So it's much thicker. The coupling is also much reduced, and you get more electrons. You get less coupling. Those two critical problems solved, right, in the 2D scaling. So of course, your lateral footprint of one string now is much larger. So that's why you need many layers to break even, right, in terms of density, right? If you do not have many layers, then this string is so large, then you do not have area density advantage. Unless you have many layers, you are going to share the same space. Okay. So also in terms of the chip performance, here many improvements. For example, here compared to the 1X node MLC from the 2D versus the first 3D. Here like the bandwidth, program throughput, and also the I/O speed increases. The most critical one is the density. So density previously is about 0.6 gigabit per millimeter square. Now you get like close to 1 gigabit per millimeter square. Question?
Is there any level for multi-level cells for 3D NAND?
Yeah, you can apply the same multi-level cell operation on the 3D NAND. 2-bit, 3-bit, or even 4-bit today. So yeah, so then at the system level, they also did some, benchmark running the real workloads, and this, have those improvements. I'll skip that. Basically, some real workloads testing. So here is the summary of this first generation, and you can, look at the table again in terms of the organization. Here, for example, how many pages, how many blocks, and so on. So then Samsung keep the progress every year, at least 2014, 15, 16, 17, 18, every year they have a new generation. They publish it in the ISCC. So for example, in the 2015, this is becoming like a 32 layer, and also here you see 3-bit per cell in this second generation. So here this is a diphoto, and then I've skipped many details, but just look at the bit density improvement. Previously it's close to 1, now it's like 1.8 gigabit per millimeter square. So like each generation you almost double the density. And then third generation, density is like 2.6 gigabit per millimeter square. And then this jump to how many layers? Let me see. Where is that? 48 layers. Okay. And then fourth generation, right? So the density close to 4 gigabit per millimeter square. And then this becomes 64 layers. Okay. So then, I would say from 2014 to 2017, Samsung lead the industry. There are almost no competitor in this space. The other companies ramp up this later, maybe 2017. Then other companies also followed. So here, then this become a race of building this skyscraper, like high buildings, high rise. So just all the companies just jumped into this competition, build higher and higher, more and more layers. Okay. This is at 2019, at that time, close to 100 layers. All the companies, the big players now can do that. So here, then what is important, then you have to etch this very precisely. So if you have some angle to etch this trench, actually you will lose the density advantage, because at the top you have to use larger area. So this is not good. So here then, because it's so difficult to etch so many layers, so that's why there's a trend to split this into 2 lithography steps. As I said earlier, you wish to have 1 lithography step to finish the entire 3D stack, but this is become too difficult. So for example, here Toshiba split this into 2 steps. First you finish here, and then you finish here. Okay, this is all staircase, 2 step as well. So this is zoom in. You can see there's 2 step, 2 deck. Okay. So here, this is a recent trend, and I didn't update this year. This year is around here, 300 layers. Okay, 300 layers. So then 2 more important innovation in the recent year. One is the CMOS under array, CUA, as I said earlier. So you want to hide the peripheral circuits in the silicon substrate, and then you build the 3D NAND on top. Because 3D NAND, as I said here, this channel is polysilicon. So you can do that on top of the single crystalline substrate. So you finish this first, and then you do the polysilicon. And then there's an alternative approach, because you heard that the DRAM industry already does the bonding, right? So then why not we do bonding here? So there's a newcomer into this field called by MTC from China. They propose this X stacking method to basically stack, let's say bond the peripheral circuits and the 3D NAND. I think the major players will also follow, actually. Samsung and also SK background, they will do that in the next few generations for the bonding. So just the 2 more slides. This is thanks to Sangwoo asking to update the date tables in the recent years, because we used to have this survey like in 2002, but then after that there are a few more publications in the field. So you see this is the latest chip published in the top conferences, and we split that into 2 slides. The first one is the TLC, 3 bit per cell, and then here, for example, you have those 300 layers from SK Hynix last year. But then you see the total capacity is the same, 1 terabit. But then this one, since it has more layers, so the chip die size is smaller. Okay, or let's say the density is more than 20 gigabit per millimeter square now. Compared to the first generation, if you recall, it's 1 gigabit per millimeter square. So over the past 10 years, it's double, like increased by 20 times, more than 20 times. So here are some other like you know, electrical data. So here the programming speed, typically like hundreds of microseconds for the TLC programming, because you have to do this write and verify. And all of them use CMOS under array. Okay. So this is a QLC, 4 bit per cell. So you can have a little bit less number of layers because you have 4 bit per cell. You don't need to build so high, but it still achieves the same 1 terabit density. But then in terms of the density here, for example, Samsung this year is close to 30 gigabit per millimeter square already, because it's 4 bit per cell, and then you don't need so large die size now. But then the trade-off here, you can clearly see the speed is slower. For example, the programming now is more than 1 millisecond, because it's more difficult to write and verify for 4 bits per cell. That will also affect the throughput. Okay, so I think that's pretty much we want to talk about today. It's a little bit over time, so I'll skip the summary, and you can read the text. Okay, all right.